Hey developers, welcome to Devcovery. Today, we're bringing you the hottest open source projects trending on GitHub, so you don't miss any tech developments worth your attention.
Today, we're taking a deep dive into a trending project on GitHub, RAG Techniques, a comprehensive collection of advanced methods for building retrieval augmented generation systems. With over 25,000 stars and growing fast, this repository bridges the gap between raw information retrieval and intelligent language generation, giving developers a practical playbook for building AI systems that actually know what they're talking about. What happens when you stop treating RAG as a solved problem? A repository called RAG Techniques, built by NirDiamant, has crossed 25,000 stars on GitHub with nearly 300 new stars added in a single day. The reason is straightforward. Most developers building AI systems know how to stand up a basic retrieval pipeline. Far fewer know how to make it actually work under real-world conditions. RAG Techniques is a curated, continuously updated collection of Jupyter Notebooks that systematically demonstrates over 30 advanced techniques for retrieval augmented generation systems. RAG retrieval augmented generation is the practice of connecting a large language model to an external knowledge base, so the system can retrieve relevant information before generating a response, rather than relying solely on what it learned during training. The project was created by NirDiamant, an AI educator with a newsletter following exceeding 50,000 subscribers and a growing ecosystem of companion repositories covering agents, prompt engineering, and production deployment. The numbers tell a clear story. 25,450, 2 total stars, 284 added in a single day, and 2,985 forks. Projects reach that fork count when developers are not just reading the code, they are actively pulling it into their own work. Here's the problem driving this project's momentum. A basic RAG system is not hard to build. You chunk your documents, embed them, store the vectors, and retrieve the top results when a user asks a question. That works well enough in a demo. In production, it starts to fall apart in ways that are genuinely difficult to diagnose. A user asks a complex multi-part question. The retrieval step returns technically relevant chunks that still miss the actual answer, because answering it requires connecting information scattered across 3 different sections of a document. A query uses domain-specific terminology that does not match how the documents were written, so semantic search returns near misses. Retrieved chunks are long and full of off-topic content, so when they reach the language model, the relevant sentence gets buried in noise. Before repositories like this existed, engineers had to excavate academic papers, reconstruct implementations from scratch, and guess which techniques would transfer from research benchmarks to their actual use case. There was no single place where you could find a working implementation of self-RAG sitting next to a tutorial on contextual compression, both runnable in a Colab notebook within minutes. That gap is precisely what RAG Techniques was built to fill. The project is organized into 4 distinct layers of complexity. The architecture reflects a deliberate pedagogical choice. Every technique is self-contained, reproducible, and built on either LangChain or Llama Index, the 2 dominant orchestration frameworks in the space. Start with query enhancement. One of the most counterintuitive insights in information retrieval is that the user's original query is often the worst possible search string. The hide technique, hypothetical document embedding, addresses this directly. Instead of embedding the user's question, the system first asks a language model to generate a hypothetical answer document, then embeds that. The intuition is that a hypothetical answer sits closer in the vector space to real documents than a bare question does. Think of it as asking someone who already knows the answer to describe it, then searching for that description. A newer variant called hypothetical prompt embedding inverts the approach entirely. Rather than generating hypothetical answers at query time, it pre-generates hypothetical questions for every document chunk at indexing time. Retrieval then becomes question-to-question matching, with 0 runtime LLM overhead. Move up the complexity ladder, and you reach Graph RAG. Standard vector search treats every chunk as an isolated unit. GraphRag transforms the document corpus into a knowledge graph, extracting entities and relationships, then traversing those connections at query time. This enables multi-hop reasoning, answering questions that require connecting CEO A to company B to acquisition C, without any single document containing all three facts in one place. At the frontier sit self-RAG and corrective RAG, known as CRAG. These architectures introduce something fundamentally different. The system evaluates the quality of its own retrieval before committing to a response. If retrieved documents score below a relevance threshold, CRAG triggers a fallback, typically a web search, to supplement the knowledge base. The pipeline becomes adaptive rather than mechanical. The practical target audience here is not beginners. This repository is built for the engineer who already has a RAG system running and is hitting the ceiling of naive vector similarity. An enterprise building a legal document analysis tool would find the hierarchical indices and contextual compression techniques directly applicable. Hierarchical indices create two-tiered structures, high-level document summaries, paired with granular chunks, so retrieval can start broad and narrow down. Contextual compression then strips retrieved chunks down to only the sentences relevant to the specific query before passing them to the model, reducing hallucination pressure and token costs at the same time. For teams building internal knowledge bases over large, interconnected document sets, the GraphRag implementations offer a path to handling relational queries that flat vector search simply cannot touch. The entry barrier is intentionally low. Every technique ships as a Jupyter Notebook runnable in Google Colab with no local environment setup required. The primary dependency is an API key, usually OpenAI. A companion directory of standalone Python scripts also exists for teams that want to extract and integrate specific techniques into existing pipelines without carrying the notebook infrastructure. The community reception has been strongly positive, which the star velocity reflects. Developers across technical forums and Reddit's educational AI community have described the repository as a reference they return to repeatedly, especially when production RAG performance degrades in unexpected ways. Criticism is present but constructive. A recurring concern is that the majority of notebooks assume access to an OpenAI API key, creating friction for developers working under data privacy constraints or cost restrictions who need open-source models instead. Several GitHub issues have flagged dead links in older notebooks, a predictable consequence of maintaining 30-plus interdependent notebooks against rapidly iterating upstream frameworks. Community requests focus on expanding coverage of newer tools like LightRag and Pydantic AI, and on adding more systematic benchmarking so developers can make technique choices based on measured latency and accuracy trade-offs rather than intuition alone. The repository's strength is also its most significant structural limitation. It is a collection of techniques, not a framework. Extracting value requires a developer who can read a Jupyter notebook, identify which technique applies to their specific failure mode, and then re-implement it cleanly inside an existing production codebase. That is non-trivial work. The gap between a working notebook and a production-hardened module is real. There is also a question of measurement. Several of the more complex architectures, self-RAG and CRAG in particular, add multiple LLM calls per user query. The notebooks demonstrate that these techniques produce more accurate responses. They are less consistent about quantifying the latency and cost increase that comes with that accuracy improvement. A team adopting corrective RAG in a high-throughput application needs that data before committing to the architecture, not after. What this repository almost certainly will influence, regardless of those limitations, is the baseline expectation for what a competent RAG system looks like. The techniques it documents are migrating from research papers into production expectations. That shift in the floor is meaningful. RAG techniques is the most complete practitioner's reference for the gap between a working RAG prototype and a reliable production system. It does not hand a team a deployable product. What it does is compress months of research and trial and error into a structured, executable library of solutions. For any team that has shipped a RAG system and is now debugging why it fails on the hard cases, this is the right starting point.
That's all for today's Devcovery. We hope these GitHub trending projects spark some inspiration for your development work. You can find all the repos mentioned in the description below. If you enjoyed this episode, don't forget to subscribe to our channel. See you tomorrow at the same time.